This talk is about grounding and bonding. I'm focused on home and mobile stations. Primarily, it's an HF talk. This was originally given at Contest University and has been steadily evolving ever since. The goal of the presentation is to discuss what ground and bond mean. We use the words a lot. We don't use them very precisely. They have a lot of different implications and meanings. And then we've got a really wide range of requirements to deal with in the ham station. And ham stations are one of the most difficult to deal with because we deal with AC safety, we deal with lightning protection, and then all this RF up into the microwave spectrum. So literally DC to daylight. So each general frequency range has different requirements. So we'll talk about what you're trying to accomplish with grounding and bonding for each of these regimes. And then this is not a cookbook talk. It's too complicated. There's too many different circumstances to say, step one, do this, step two, do this, step three. Doesn't work that way. So this is kind of a toolbox talk where I talk about the requirements and then techniques and the various issues that you come up with. And you go home and you go, okay, so that's what he was talking about. Here's my budget. Here's my circumstances. What can I do? And one of the important things I want to keep coming back to is one common, well-done system satisfies all these requirements. You don't have to have an AC safety grounding system and a lightning protection system and an RF management system. They are all basically the same problem, and you can deal with it with one system. You build it right the first time and it'll take care of you. There are some special issues associated with mobile stations, and I'll touch on some of those as well. And there are comprehensive resources at the end of the talk. If you would like a copy of the slides, including all the URLs and all that stuff, you can email me at my qrz.com address. Be happy to send you the PDFs. So it's not copyrighted, and you can basically do whatever you want with it. There's a lot of good reading material for the interested reader. Now, the ham radio references, the ARRL handbook and the ARRL antenna book have a lot of this material in it. Since I was the editor up until the most recent editions of these things, I was able to get a lot of the material into the book. It's condensed. You'll find it in the ARRL handbook back in the building a station and in the ARRL antenna book building antenna systems chapters. Ron Block in R2B is one of the polyphaser original guys, and he wrote a very good series of articles in 2002 QST called Lightning Protection for the Amateur Station, where he discusses what lightning is and how to plan for lightning protection. These are publicly available. They're on the ARRL website. You do not have to be a member, although I hope you are. You can go in there and search for this and it will come right up. K9YC has written a number of really good tutorials over a wide range of topics, and Jim has two that I recommend all the time. First one's called Power, Grounding, Bonding, and Audio for Amateur Radio. Sounds like my talk. He really gets into it from the perspective of a retired audio engineer and active ham. His second is the Ferrite Bible for hams, RFI ferrites and common mode chokes. Just go to k9yc.com/publish or just Google K9YC tutorial and you'll find it. W8JI, Tom lives on a mountaintop in Georgia with 300-foot tower. And so he knows a lot about grounding and bonding and lightning. So his website is another resource for you. And for mobile stuff, the best website out there at the moment is K0BG, Alan Applegate, K0BG.com. So those are the good ones. And then I'm kind of partial to this guy, Grounding and Bonding for Radio Amateur. It's not a big book. It's about yay thick. The goal was to collect a lot of the information that was out there for AC wiring and lightning and dealing with RF in your shack and all that kind of stuff. The information was dispersed. It was very difficult to find out what to do and how the different types of recommendations related to each other. So the book brings them all together. It was reviewed by a number of experts, including Ron Block and Dale Svetnoff, who's another lightning consultant out of the Midwest, plus the ARL lab and Jim Brown. And so those guys were really good and kept me out of the weeds. So that's a big endorsement from those guys. So like this talk, it's a toolbox for you, but it covers a lot of the issues and hopefully explains them so you can understand them. So let's jump in here. What is ground anyway? The word ground is wildly overused, and it has different meanings, and it can be a noun, which means a thing, an earth connection, that is the ground, or it can be just a local reference potential. They talk about ground sometimes in airplanes. They're not dragging a chain, so what they mean is the local reference voltage that everything is based on. It can also be an action where you want to ground something, like you want to short something to the reference potential or to the earth. It can be an adjective to describe a type of a thing. And so you have ground conductor, ground system. And you can use all of three senses of the word at the same time. And I've listened to people having conversations about grounding, and they're both nodding up and down in the right direction. And then I realized they're really talking about completely different things. So you have to be very careful when you say ground, what you mean. The British have taken the word and they use the word earthing. When they mean connect something to a ground rod, they say earthing. And so that helps explain things. Couple of myths about grounding. A lot of times we treat the earth as a kind of a magic 0-volt reference where electrons go into it and bother us no more. And that's not the way it works. The earth is got resistance. It's a distributed surface, so there's inductance, there's all kinds of things. If you dump a lot of current into it at RF or lightning, it will not magically and safely disappear. It will flow and create voltage drops, and we'll get into that later. It's the same thing for a vehicle body. It's not a 0-volt reference. We have to stop, or at least be very careful when we're using the term RF ground. There really ain't no such thing. RF covers a wide range of frequencies. And so trying to create a 0-volt or at least a common voltage across a wide frequency range is a very difficult thing. So you can really only create this reference voltage at RF on a limited number of frequencies, and treating something as the magic RF ground is really a good way to get into trouble. So I try not to use the term. Another is ground loops. Everybody says, oh, you can't have any ground loops. Ground loops are terrible. They cause this, they cause that. Any conductive path around a loop through pieces of equipment or cables or whatever, that's a ground loop. And if you go and you look in the back of even a small ham station, there are literally dozens of ground loops. There are all kinds of these paths. So you can't get rid of them. First of all, they don't really cause all the problems that they get blamed for. And what we have to do, instead of trying to get rid of them, we manage them. So we manage them by reducing the area and through bonding, which is what we're going to talk about in a minute. Another term is single point ground. This really came out of the AC utility field. And what it means is an electrically small contact point so that current does not circulate within a power system. And so you're trying to connect everything together so that it's at the same voltage, which is a bonding thing that we'll talk about. But the idea in the AC was to prevent error currents from circulating in the system. So single point means electrically small. If you're at AC, 60 hertz, the wavelength is about 5 million meters or 50 million meters or whatever it is, 50 million, I think. So something can be the size of a football stadium and still be pretty electrically small. But at 20 meters or 6 meters or whatever, electrically small is drastically smaller. And so you have to be careful about throwing the words single point ground around. Each set of requirements that you encounter, the AC, the lightning, the RF, they use ground differently. You've got to be careful about how you use them. Okay, bonding. We're all bonding here. Yes, that's good. But when you go and look up the bonding definition, all it is a connection intended to keep 2 points together at the same voltage. The key concept for bonding is that everything that's bonded together goes up and down at the same time. It goes up and down together. It's like a floating dock. All the dock and the boats go up and down together when a big wave comes along. And it's the same thing in electrical bonding. You want all of the bonded stuff to go up and down together. That prevents shock hazards from voltage differences. If there's a fault, it prevents these destructive voltage differences caused by lightning surge when point A goes to 10,000 volts over point B just for a second. But lightning's really fast and it can create really serious destructive surges of current between the equipment. So by minimizing the voltage differences, you minimize the lightning surge voltage and current. And then RF pickup from your antennas is another problem. And you're really close to your antennas. You're within a wavelength or two. You're in the near field. And what causes RFI is not the voltage, it's the current. It's current getting into something in your station that it's not supposed to. And so if you can limit the voltage, you can limit the current. Current flows in response to a voltage. So by bonding and keeping everything at the same voltage, you minimize voltage differences, so you minimize the current. And for bonding to work, it has to be a low impedance electrically short connection across the frequency range that you're working with. That could be AC, it can be lightning, which is the low AC all the way up to a megahertz or more, and then RF that we use, which is down in the medium frequency range all the way up into UHF and microwave. So you want it to be short so that it doesn't start acting like an antenna or a transmission line, and it has to be low impedance. That's low X and low R for bonding to work. Now, the different ranges emphasize resistance or inductance. We'll get into that. It also has to be heavy enough to carry the expected current. If you're talking about bonding for lightning protection and you're talking about your antenna system, you have to have big wires, what I call the BAW, big ass wire. That's why they're so big. They have to carry kiloamps. To a circuits guy, the concept of kiloamps is scary to me, and it should be because there's a lot of energy there. And in a lightning strike, even an indirect surge, you can get a lot of current. So the bonding conductors have to be heavy enough to carry it without vaporizing. And it also has to be mechanically sturdy, especially outside. If you're going to bury these things, if you're going to put them in the yard, if you're going to put them around your towers, they're going to suffer from frost heaves. You're going to drive across them. You're going to forget they're there and dig them up with the rototiller. Don't ask me how I know this. And all sorts of other things. That conductor has to be heavy enough so that it will withstand all of that. It's got to jam the rototiller or the shovel and let you know. If you cut it, you may never know that you don't have a ground connection. So it has to be out there. It has to be sturdy. And that's why the building codes specify that kind of thing. Inside your station, what do you use for a bonding conductor? The recommended thing, the standard thing, is some kind of solid metal strap, copper, bronze, brass, whatever. 20 gauge is the standard, about an inch or an inch and a half. And heavy wire also has almost an equivalent surface area to the heavy strap. That number 14, number 12, all that Romex that you refuse to throw away because you're going to use it someday, and it's in that box in your garage. This is the perfect application for it. Get it out, strip out the conductors. These are perfectly good bonding conductors within the station. You can use that flat weave tin braid, the silver stuff, if your equipment moves around or if you need to move the connection around. But protect any kind of a braid from moisture and chemicals. In your car, you'll see this braid used for DC connections, and they don't really care so much. They're worried about resistance, but not so much impedance. If you use this strap in your car, your vehicle, for grounding and bonding, you need to protect it from moisture and chemicals, and they have plastic coated braid. Do not use exposed braid from old coax. You say you've got this piece of old coax, I'm going to use this as a grounding strap or whatever. That's fine, but what happens? You've got to take it out of the jacket, peel off the jacket, then you loosen it up so you can take the center conductor out, and you're going to use that as high voltage wire, aren't you? Okay, so once you take that braid out and you loosen it, all those little connections, that you look at it and they're all over, under, that sort of stuff, they start coming apart. Also, the braid is now exposed to oxygen, it's exposed to water. Both of those things are bad. So you got 3 strikes on you: loose connections, corrosion, and water. All of those things are bad. So leave it in the jacket. Just treat it as a BAW, big ass wire. Put some pigtails on each end, put a terminal on each end, waterproof it, and you've got a perfectly good ground conductor. But the minute you take it out of that jacket, which is there to protect and compress it, it starts to degrade right away. So when you do this bonding, when you use these proper conductors and that kind of stuff, short, direct, as much as possible, this works in your favor. It creates a perfectly good grounding system, grounding and bonding system for AC safety, lightning protection, and RF management. Okay, let's talk about AC safety for a minute. I think most of us could run a branch circuit or install a light switch or build our own power boxes. Some of the advanced students might be able to do a 2-way light switch. Oh my gosh, okay. But if you're not really sure what you are doing, and I know we're federally licensed ham radio operators and therefore know everything, go out and get a how-to reference. This one on the right side of the screen, the Black & Decker complete guide, is really good. It's under $20. You can get it at the big box stores or you can get it online. It takes you beyond the branch circuit. It says what to do and what not to do in wiring your house, and it shows you how to wire all these strange things that are out there available for home wiring now. This is a very good book. There's probably a half dozen of these things out there. Get one and follow it. The other book that I recommend is this thing. It's a giant book. It's called the NEC Handbook. Now, the NEC itself is a little book. It's a small book. It's just a book of rules, and it doesn't tell you why or whatever. It's just kind of like a law book. The handbook, on the other hand, the reason it's so big is that it gives you rationale. It has pictures. It explains why you do and do not do certain things. It's available at the library. You can get old copies for like $30-40 online. And they're big, but they're not that expensive. There's only 2 articles that hams are basically interested in mostly. Article 250 is about grounding, and Article 800, and those are chapters, is about antennas. So you can either go copy the appropriate parts or you can download the appropriate parts, however you get it. But the NEC Handbook is a very useful reference. It has special rules for subpanels and outbuildings. And a lot of our stations or auxiliary equipment is on a subpanel in a garage or a shed or a shack. What do you know? Someplace out in the yard. There are very special rules for wiring and grounding these things so you don't create shock hazards. And people are electrocuted every year because their outbuilding or their garage isn't grounded properly. And so they're standing there barefoot on the concrete slab. Concrete is amazingly conductive. Standing there barefoot and they touch something and there they go. So follow the rules for subpanels and outbuilding. Can't stress that enough. And then at the end of it, if you do anything complicated, why don't you hire a pro electrician, one of your local licensed guys, to come over and take a look at your work? Pay them for an hour. It's not that expensive. Inspect it. Maybe they'll save you a lot of trouble. They say, you really should do it that way, or here's how you should do it, or this is not up to code. Local code is the law, and it's not there to make your life miserable, although sometimes it does. It's there to keep you from burning your building down. The NEC is developed by the National Fire Protection Association, and that tells you a lot right there. Your local code is the law if you want to get paid by your insurance company in case there's a problem, or if you want to get insurance twice, you got to have some kind of confidence that your electricity is handled properly. So follow the code and know what you're doing, or hire somebody that does. Let's talk about lightning protection. Excuse me. Okay, lightning comes from up there, way up there, 30, 40, 50,000 feet. So by the time it gets to the ground, it's pretty well decided where it's going to go. You can't steer lightning. You can't say, oh, I'm going to make sure it goes over there. It'll go where it wants. But you can help Mr. Lightning make good decisions, okay, by the way that you build your system and install it. What does lightning want? It wants heavy, direct paths to the ground so that it can dissipate whatever charge imbalance there is, positive to negative, whatever. The idea is to equalize the charge imbalance. So the charge has to get into or come from the ground, and there's a lot of it. So give it heavy, direct paths wherever possible. And for lightning, because it's an AC kind of event, inductance is more important than resistance. Down at AC, we care more about resistance. We want to make sure the safety and the ground conductors can handle any kind of a fault current, so the protective devices will open up and remove power. For lightning, which is an AC thing, we want low inductance. Even a straight piece of wire has inductance. A 1 foot piece of number 12 solid wire has about 330 nanohenries of inductance. And if you hit it with a kiloamp per microsecond pulse, it's going to develop 712 volts approximately from one end to the other, just from the inductance, not the resistance. So inductance is very important. You want low inductance paths in your lightning protection system. And all of those paths, as much as possible, should be outside, out there somewhere, outside your residence or the building. Don't make it easy for lightning to go through your station, through your house on the way to the earth. Don't put grounding conductors in the crawl space, in the basement, in the attic, in the walls, anything like that. Make sure it's outside. It's inconvenient sometimes, but you do not want a lightning path through the house or the station on the way to the earth. Let's talk about single point ground panels. Now, here's a place where single point is really accurate. The idea for a single point ground panel, usually this is an entry panel for the ham station, is for it to bond all of the entry paths, all of the grounds together at one spot, very, very close together. Most entry panels are a couple feet by 18 inches or something like that. That's pretty short at most of the ham frequencies that we care about. And then that is connected to your perimeter ground. We're going to talk about perimeter grounds in a minute, but that's the grounding system outside the house that gives those heavy direct paths into the earth. So your single point ground panel bonds all of the grounds together, connects them to the ground system outside. And all of your protectors, your lightning arresters, your data line, your phone line, your AC service, your protectors are mounted on this panel, even though it's somewhat inconvenient. They are mounted on this panel so that they fire at the same time. And when you fire at the same time, that minimizes the voltage difference. You don't want one protector way over here and another protector way over there, because what that creates is big transient voltages between different parts of your system. And those can be multiple kilovolts. And it doesn't take very long for a multiple kilovolt electrical pulse to generate a lot of destructive current. It just takes microseconds. So you want all of your protectors together so that they fire at the same time. And that's not just your lightning protectors for your coax. It's all these other different kinds of connectors or protectors. Sorry about that. Okay, so here's a typical single point ground panel, sort of a schematic view, where you've got a metal panel. It doesn't have to be copper. It can be aluminum. It can even be galvanized steel, whatever. It's a big common metal panel. And everything that protects your system is mounted on this panel. That includes an AC power protector. Yeah, it's mounted on this panel too. So there's your classic, I'll wave my cursor around here. Here's the classic lightning protectors. Here are protectors that go to a rotator or some kind of control line. Your data or phone lines, all these service boxes, they have a rule that they have to be connected to a ground system. So they'll either put in their own ground rod or they can connect to your ground system, which is what you want. If you can make everything come into your house at the same point, usually close to the AC service entry, that's the best thing. Although it seems to be federal law that the ham station is all the way on one side of the house and the AC is on the other. But increasingly, more and more, all of these systems come to the house at the same point. And it's so that they can be protected with this common ground system. Now, you've got one group of cables that are protected. They're on the uphill side of the protectors. And then you've got another group of cables and wires that are unprotected. Okay, so you want to keep your unprotected stuff away from the protected stuff. And I know it looks really nice if you bundle it all together and you put the tie wraps on it and you put it in the conduit together and all that, and it looks good. But what happens really in that case is the lightning comes along and says, oh, I'm just going to jump straight from this cable over to this unprotected cable. I'm just going to go around that protector stuff. And so what you do is you defeat your protection by bundling all the cables together. So keep the protected stuff on one side and the unprotected stuff on the other. Here's an example of a single point ground panel. This is from K4RO, and Kirk lives on a hilltop west of Nashville, lots of thunderstorms. Every time a thunderstorm came through, he was losing some piece of equipment in his antenna system, blow something up, a filter, a switch, whatever. And so he finally said, okay, I'm doing the single point ground panel thing. And he's got a big panel of aluminum here. This is in his garage, and his shack is directly above this panel. Then he put everything on the switching output side of his antenna system on this panel. Here is his big ass wire, BAW, goes outside. I think it's number 6, like we all use, and that goes outside to his ground system. Okay, since he has installed this stuff, he has lost exactly 0 pieces of equipment. So this has been several years, and it makes him a very happy camper not to have to worry about things when he hears thunder. Here is an example of a single point ground panel at a tower base. I have a station in rural Missouri, it has 3 60-foot towers, and it's kind of on a high spot. It's not on a mountaintop, but when I bought the property, I walked around it and I saw a lot of burned trees. And so I call it the Crawford County Cumulonimbus Discharge Facility. And I know that it gets hit on a regular basis. So each one of the tower bases has this single point panel. You can see that there's a coax switch. This is a MFJ or Ameritron RCS4L, which means it has the lightning protection gas discharge tubes in it. You can see the main hard line coming in, and then antenna wires, cables coming out of here. Each one of these is in about an 18 by 18 by 10 fiberglass electrical box I bought surplus online someplace. I created my panel, piece of aluminum roof flashing right here. It's attached to the box. Here's my BAW ground wire right here. It's connected to the coax switch, and it goes to a ground system outside. And now I'm going to save you some serious money. You can see these little guys right here. These are gas discharge tubes. You can buy them from Mauser or whoever in quantity. They're the smallest ones that are made. They're 75 volts. And what I'm going to save you money on here is this is the rotator control cable right here. It's not the fancy, expensive 2 big conductors, 6 little conductor, multi-conductor cable that we all grew up with. This is 10 conductor irrigation system control wiring. It's number 18, 10 conductors. 2 of the conductors are paired up for what we call pin 1 and pin 2, the solenoid circuit of a standard rotator connector. This is sheathed in bury ready PVC. It's made to be buried in the ground. And it's way cheaper than the fancy rotator cable. Save your rotator cable for rotator loops, stuff in the shack, things like that. And so I just run the cable in. I put a gas discharge tube on each line, and then here's the cable that goes out to the tower. Okay, let's jump back a little bit to this perimeter ground idea. The idea, and this is not just a suggestion, if you read the NEC, all earth connections shall, there's no wiggle room, shall be bonded together. It's required, and you do not want multiple external connections that are not bonded together. Well, why? Okay, so you've got, here's your electrical panel, here's your phone service, here's your TV, cable, satellite, whatever. You've got an antenna on the house maybe, and everybody's got their own ground rod, just like you're supposed to, right? Not quite. Okay, you have to bond those together. If you do not bond those things together, then what are they connected together with? They're connected with dirt. Okay, what is the resistance of dirt? It's kind of high. If you measured the resistance between 2 ground rods, you'll get 10 ohms, 20 ohms, 50 ohms. And that's not good, because if you have lightning that strikes anywhere in the vicinity, whether it hits your house or your power line or just nearby, you can get thousands of amps flowing through the ground. And thousands of amps times 10 ohms is tens of thousands of volts. And so you can have, even though they're grounded, you can have tens of thousands of volts between these different systems in your house. And that's when you hear stories like, I was minding my own business, there was a thunderstorm, I was sitting in the living room, there was a big flash outside, and suddenly a big green arc jumped from my computer to my home entertainment system, and now nothing works anymore. Okay, well, it's because the grounds were not tied together. So outside, all these ground rods shall be bonded together with a heavy conductor. Number 6 is about the smallest that's allowed. Some codes require number 4, number 2, whatever. Get your ground rods out, get a ground rod pounder, or hire some guy to go out and pound them in for you, and put in a ground rod every 2 times the length of the ground rod. You got 8-foot ground rod, then every 16 feet. Outside the house, connect them all together as much as you can. You may not be able to go all the way around the house, but do as much as you can. That's sort of a protective ring. And that's called a perimeter ground. Okay, the other thing we talked about was don't create paths for lightning through your station. So here's a typical example. All right, here's the tower outside, and the lightning comes, and either it hits the tower or it hits nearby or something, and you get a big lightning surge. Here comes the current surge down the tower, and it says, oh, here comes some feed lines. I'm going to follow them. Here's my nice entry panel. It's connected to a ground rod, so some of the current's going to go there. but the lightning's going to go like any other current. It's going to flow in every path available to it. Well, here's a nice path. You've got all these heavy cables that go into your station, and your station is plugged into a branch circuit, and the branch circuit has a ground in it, and that goes over to your AC service entry, and there's a ground rod there. So you've given lightning a tremendous path right through your station, through your AC service to the ground. And that can cause a lot of damage. So don't do that. What you do instead is you protect your AC path. You put all your protectors on this single point ground panel, and you have a very nice perimeter ground system outside. Multiple ground rods. If your tower is close to the house, say 50 feet or less, you want to bond that up there too. And so here comes the lightning surge. This time it hit the power lines, which is quite common. Comes in, says, oh, look, I've got this really nice perimeter ground system. A lot of heavy direct paths to the earth. And, well, there's also an unprotected AC circuit. Yeah, well, I'm going to flow over here, but here's my AC power protector. So instead of flowing into your radios, that surge goes through the protector and into the ground system. So the idea is heavy direct paths outside. And if you want to add extra radials to your ground system in your yard, that's just dandy. But don't give lightning its main path to go through your station on the way to the earth. Here's a typical lattice tower, Roan 25. We've all seen this picture in the handbook multiple times. You're looking down on it. You've got a ground wire, a ground rod for each one of the tower legs, and they're connected together with a ground ring. Okay, as long as you got the guy with the backhoe out there, have him drill another 30 feet, just scrape another 30 feet of trench. It doesn't have to be 6 feet, just 18 inches will do, and put in a heavy radial with a couple of ground rods in it. And that will really, really help ground your tower. Also, bond your feed lines to the tower every 50 feet. Remember that number 12 wire that had 700 volts across it from a lightning strike? Your tower in a lightning strike can develop 50,000 to 100,000 volts between the top and the bottom just from the lightning and the inductance of the tower. And that will blow your coax up. It will damage it. It'll do all kinds of nasty things. So bond your feed lines to your tower using a bonding bracket or kit every 50 feet. It's a pain in the neck. You have to do extra weatherproofing, but it's worth it since you don't have to replace cables all the time. If you've got an insulated base tower, put a little spark gap down at the bottom. It can be as simple as a spark plug or just a couple of wires that cross and make them about a millimeter or two so that lightning will jump across them instead of going into your station. Okay, let's talk about RF in the station. First thing you got to realize is everything in the station is an antenna. Absolutely everything. Yeah, your antenna's out in the backyard, but you're in the near field. What's the wavelength of 40 meters? Trick question. 40 meters, that's about 120 feet. If your 40-meter antenna is less than, say, about 200 feet from your station, you're in the near field of the antenna. And even if you're not right in the near field, you're really close. So you're going to pick up a lot of RF. Every piece of wire, and you are conductive, so you're going to pick it up too, is acting as an antenna. So you're going to have RF in the station. Again, forget about an all-band RF ground. That doesn't exist. There's no 0 volt anything. What you want is concentrate on bonding. So you have 0 volt difference. You don't want the differences. Whatever that voltage is, you want it to be the same everywhere in the station. You do that with bonding with electrically short conductors. That keeps it all at the same voltage so you don't have current flowing because of RF voltage differences. If you've got an amplifier, not only do you meet your neighbors, but you also have high RF field strength, which requires extra attention to bonding. And it really helps a lot if you create a common reference plane, which is basically a fancy word for a metal sheet, under your equipment, or some kind of grounding bus along the equipment. You've seen this picture in the handbook for many years, where we have a bonding bus, an RF bonding bus. Usually it's a piece of 1/2-inch copper pipe. You can also use aluminum angle, anything that's good and conductive, and you put ground clamps on the pipe. You can either use the little acorn ground clamps, or you can put sheet metal screws in the pipe. Do not use the regular stainless steel hose clamps. They're not made for this, and they loosen up. They're made for metal to soft, squishy stuff, connections, hoses. So use sheet metal screws or ground clamps, or what I've started using is these little grounding bars. They're available in 7, 9, 17, 23, all these different positions. They go in AC service panels, and they are the neutral or ground bus. They're not expensive. They're made for this service. You can bolt them right to the reference plane, and that works really well. So the idea is to reduce RFI from this common mode current that is picked up and conducted on all the cables. If you don't have voltage differences, you won't have current flow. And this also reduces sensitivity to how your station is assembled. So you don't get into a situation, well, to operate 15 meters, I have to sit over here and I can't put my feet on the floor and I have to hold one thing or I get an RF burn. No, this makes it all one electrical thing. That's what bonding does for you. We talked about ground loops before. What causes a ground loop to pick up and a voltage and cause a current is the area. The bigger the area of the loop, the more voltage it's going to pick up. So you want to minimize cable length and you want to minimize loop area, those two things. Use short or coiled cables. It seems like you can't buy cable, data cable or RF or whatever, that's less than about 3 feet or 18 inches. But use the shortest cable you can get. If you've got a long cable and you don't want to just have it laying around all over the place, coil it up in a figure 8 pattern, and that minimizes the inductance. And then you lay everything on the reference plane or connect it right along that RF bonding bus. You minimize the area, you minimize the amount of RF you're going to pick up. Always use shielded cables for anything, audio, RF certainly, all control stuff. About the only thing you can get away with using non-shielded cable for is power. And all of your grounding conductors have to be short straps or wires. Here's an example. This is at my station. This shiny thing here, it's roof flashing. It's a piece of 12-inch roof flashing that I took my unfortunate Costco banquet table, and I just used sheet metal screws to attach it at various points along the table. All of the cables lay on that. There's a bonding bus in the back, and everything's connected to that. And aside from a very few problems, and I'm running 2 stations with full power outputs, I just don't have any RFI or RF-induced problems. Ground system review. A single ground system, short, heavy, direct connections, satisfies all of the requirements for these 3 things. You want to bond all of your grounds. You don't want your AC safety ground separate from your lightning ground, separate from your RF ground. Don't do it. They all have to be connected together. Keep your protectors together so they all fire at the same time and minimize voltage difference, and create your perimeter ground outside to keep your lightning current outside the building. Let's jump over to mobile stations. The RF issues can often be really intense because you're in the antenna. Yeah, the car is part of the antenna system. You're in the car. Your radio's in the car. You're part of it. Okay, there are also some special power wiring considerations. Bonding in today's vehicles is a lot harder than the old days. And what about mounting the equipment and the antennas? So you want to consider where your fuses are, ampacity, which means how much current the wires can carry, and the voltage drop when you're pulling the full 12-volt current through these conductors. You always want to fuse both leads and use heavy wire. The negative lead must be fused as well. So if there's a fault in the system, the fault current, which can be substantial, doesn't find its way back through your radio and through the negative lead to the battery. That's basically a fire. It will burn up your radio for sure. It can really damage your car. Remember that 12-volt radios aren't really 12 volt. They want a minimum of 11. What they really want is 13.8, which is the charging voltage of a lead acid based automotive battery system. They're designed for 13.8. They can go up to 15. Give them a lot of voltage and they'll be happy. If you start getting down below 11 volts, you get some really strange behavior from your mobiles. So you got to take that into account. Especially when you're dealing with voltage drops, you want to use heavy wire and you want to use connectors that do not have a lot of voltage drop. Okay, and then we got to talk about where do you connect your power return and battery monitoring systems, and then there's these weird DC booster things. Okay, power return. If you've got one of these dudes on the negative terminal of your battery, then you have what's called a battery monitoring system. This is particularly common in newer cars that have what's called engine idle shutdown. If you pull up the stoplight, the engine stops. It's an emissions management thing. But then when you get ready to start up again, it cranks over the engine and away you go. Okay, so to keep the battery fresh, because it gets used a lot in these systems, the battery monitoring system counts every electron that goes back and forth out of the battery. That's what this little thing is here. And so your computer will sense how much current's gone in and out, make sure the battery is fully charged. Well, if you connect your negative from your radio here, what you do is you bypass that system. So the computer doesn't know about your radio current, and eventually you'll discharge the battery because you fooled the computer into thinking less current was taken out than really it was. So what you do is you got to go dig down into the bowels of the earth and find this big heavy chassis ground point where the starter motor reconnects, and that's where you connect your fuse power return system from your radio. If you want to minimize pickup, twist your power cables together and that will help minimize RF pickup. But home run wiring is what it's called, and you want to connect down here. So connect there and not to the negative power terminal on your battery. Then there's these boosters so that your car, all of your electronics doesn't go off and back on every time you come to a stoplight in these cars. They use DC to DC boosters that keep the voltage to the system exactly 13 point whatever. So they even out that voltage. Okay, do not use those boosters for ham gear. They're not rated for it. They do not want to provide an extra 7, 10, 20, 25 amps for your transceiver. Get your own doggone booster, okay? Wire it in just like the other ones, same chassis ground point, home run radio, and run your gear off a DC to DC booster. It'll run better. Everybody will be happy. Bonding in mobile stations can be a real problem because the body components of the car aren't always even metal, and so they're not always well bonded. You can't just drill a hole someplace and say, it's metal, so it must be a ground system of the vehicle. Don't. You've got to be very careful about where you connect your ground returns. Don't use the subsystem ground points. I mean, for the computer system or some kind of controller, what happens is you inject all that radio current into that ground point, and the voltage can go up and down a little bit. That can confuse or upset your subsystem operation, and it looks like you've got RFI. You don't have RFI, you have DCI. You have DC injection into that ground point, causing the voltage to go up and down when the subsystem doesn't expect it. So don't bond to these points. Go all the way back to the power source. And when you bond to the body, you create all these new strange return paths for DC and RF paths. So it can be very difficult. You want to bond to the body for antennas, but not your DC stuff. Anytime you make a contact out in your vehicle, use these anti-corrosion compounds that are designed for vehicle use, and they protect the connection, and that keeps them from corroding over time. Sometimes you put in a new system, it works just great. The months go by, particularly the winter months, and there's a lot of thermal cycling, there's salt, there's all this other stuff, and strange things start to happen. Use these connector protection compounds when you're wiring in your vehicle. Another thing that you can do is mount your equipment in these standalone racks, these little mini racks, and then everything's bonded right inside this rack. You don't have to worry about using the car, and then you can make one connection to the vehicle if you want to. Truck toolboxes, carry case stations, all this kind of stuff. The only problem is if you can take it in and out of the car easily, well, so can somebody else. So you have to worry about the security of your station equipment if it's in one of these standalone systems. But it is all nicely bonded together, and it generally minimizes RF problems. Another thing is you don't have to bond this stuff to the vehicle. These radios, particularly mobile radios, are designed to work completely independently of being connected to the vehicle, except for power. I mean, we've all done it. We go to the Hamfest, we buy this nice mobile transceiver, and then we shove it down between our seat and the transmission hump, and we go, oh, we'll fix that later. Well, it's a temporary thing, and you know what temporary means in ham radio? It means until I die. So it's going to be there in your vehicle forever. There's really no need to bond that to the vehicle. It works just fine. Control heads are the same way. Unless the manufacturer of the radio tells you to bond the control head to the vehicle, don't do it, because you're creating some other kind of weird path that was not in the design, and you can cause problems. Mechanical security, please don't let your radios flop around in there. Tie them together. Even the one that's down in between your seat and the transmission hump, why don't you put it under the seat? Take the control head out or something, but tie that sucker down so that when you are in an accident or anything, you don't have this multiple pound metal object flapping around in your passenger compartment. And there are airbags everywhere now. Side bags, top bags, front bags, and anything you place on front of one of those panels, if there's an accident and those things fire, whatever's on front of that panel is going to come at you at about 100 miles an hour. So you don't want a control head or a microphone coming at you at that kind of velocity. So find out where those airbags are and don't mount anything there. You can use the channels under the door trim and stuff like that. There are secret passages in your vehicle. Use them, because that's what the manufacturers do. They shield your cables from direct RF pickup. It protects them mechanically. Get a service manual, read through it in the body sections like a Chilton's or something, and you can find out where these things are. Also, there's a lot of hidden wiring that you don't know about. So when you're drilling holes, only drill a little ways so you don't drill into a control cable, or worse, 12-volt power. Service bulletins and repair manuals are good stuff. When you're mounting an antenna, bond the antenna to the body right at the antenna. Well, here's my helper. The through panel NMO mounts are probably the best. Motorola did a lot of work with those. They don't really work at HF, but the NMO is your best above the HF. Lip mounts that go on to hatchbacks and trunks, they need an additional body bond. They've got these little set screws and stuff, but put in some extra screws and a big protected bonding conductor to the nearest tie point. The paints and coatings on vehicles are really good today, and they will, you think you're biting through them, you may not be. Mag mounts, they'll keep your antenna on the car, but at HF, you only get about 100 picofarads per magnet. So you don't rely on the magnets as you're coupling to the body. What if you do, what you're really doing is you're saying, okay, I'm going to make the coax shield part of the antenna. So you get a lot of common mode current that conducts it right back into the passenger compartment where the radio is, and you get RF problems. So run a separate bonding wire from wherever the mag mount is over to the nearest possible point, maybe in the door or window frame or something in the trunk or somewhere on the body. So you've got a good solid connection. And when you're decoupling stuff at the antenna and the radio, ferrite cores type 31 at HF are your friends. See Jim K9YC's tutorial. If you're buying a new car, talk about an upfit package, which this, hey, take this vehicle and I want to put two-way radio stuff in it. They have packages for almost all of these cars. If your salesman doesn't know about it, ask to talk to the fleet sales department of the dealership. They will know all about it because they want to sell cars to public service and commercial vehicles, and those often have lots and lots of radios in it. The manufacturers have made it easy for this to happen. Your service department will help you. Your manufacturer service bulletins will help you. And, you can always just take your radio to a car audio or two-way shop and say, here, put this in my car. And they'll do it. They have all the little parts and the wires and all that kind of stuff. Plus, they have knee pads and their backs don't hurt, and they have nice warm shops to work in. It's money in the bank for you, and it's done professionally. So that kind of wraps it up. I've got a couple of minutes here for questions. Happy to answer them. Like I said, email me if you want a copy of the PDF slides. So do we have any questions? I put you all to sleep. I baffled you.
I got a question.
Go for it.
I don't know if I'm on the camera. Anyway, awesome. Love your book. Okay, so I have on my station, I have a metal pipe behind where the radios bond to it.
Yeah.
Then down in the garage, which is right below my operating desk, I have that's really where my single point connection panel is, where my arresters
Yep.
are located. What do I bond that copper pipe down to the single point?
You absolutely do bond to that. If we go back to that K4RO thing where he's got the single point panel in his garage underneath his station. You go up in his station, he's got a big bonding bus up there. He's got, it's a 2-radio full power station, so he's got a lot of RF up there. It's all bonded together, and then a big bonding conductor goes down to that single point ground panel. So you definitely want to bond it. I would use just a piece of heavy strap. Go get some copper roof flashing or something like that, and just run it down below the floor into your garage, and that'll do the trick.
Thank you.
And I'll touch on second floor stations. I'm sitting in a second floor station right here. Everything is bonded together, but you're so far above the ground that a connection to an outside ground rod doesn't really make a lot of sense for lightning protection. There's too much inductance. So the idea is to bond everything, just treat it as if you were in a plane. Everything gets bonded together in your station. Run all of your cables down to ground level. That's where you put protectors right there at a ground system. And then run the protected cables back up the side of the house to the station where they come in. That's my recommendation. It's not always possible, but you do what you can. Any other questions?
Okay, I have one more.
Yeah.
My tower is 75 feet away. I have buried my feed lines in conduit. I have grounding at the tower. Do I need to bond the tower to the house? Bonded ground rods?
It will not hurt, okay, to do that. But once you get up beyond, there's no definitive number here. But once you get beyond about 50 feet, the inductance of that conductor is so high that it doesn't really buy you very much to bond. Now, AC and very low frequencies, it doesn't hurt anything. And so it helps tie everything together. NEC allows you to use the outside conductor of feed lines, i.e. the shield of coax, as the grounding conductor. So you already have a pretty good grounding conductor with the shields of your lines that goes to your entry panel. But if you want to run an extra ground conductor, I would say a bare one in the ground next to that conduit and goes to your home system. That gives you a lot more ground surface, so that's good. And it doesn't hurt anything. So, but it's not required.
Thank you.
There we go. I see Rob. Hi, Rob. Rob Sherwood. Okay, so That is my cue. That's that big hook over at the right side of the stage coming out. Okay, so gentlemen, thank you very much for your attention. I enjoyed talking to you, and email me if you want the slides. 73.